Hello, my name is SBrody, and for my inorganic research survey, I chose the topic of graphene, a survey of applied synthesis through chemical vapor deposition or CVD techniques. So, as an introduction, in the modern endeavor of technology, the topic of scale is intrinsically limiting. Robust material properties nearly independent of such scale are being investigated for two-dimensional or 2D compounds such as graphene. The dense sp2 hybridization and planar structure of this organic monolayer afford it superior conduction and visible absorption through surface Dirac electron behavior, as well as mechanical paramount. It also undergoes self-repair and functionalization under conditioning. These properties have been employed chiefly by the electronics industry. Originally discerned by micrometer scale mechanical exfoliation from natural graphitic surfaces, synthesis techniques have advanced to scalable growth methods that limit application. Among many such techniques, chemical vapor deposition, or CVD, demonstrated distinct layer purity, greatest area at centimeter scale, as well as arbitrary substrate transfer, which all contribute to effective electronics application. This CVD process was optimized by the reviewed experiment conducted by Lee in 2009, essentially using methane gas pressurized onto copper foil substrates under isobaric and isothermal conditions. Produced films were exfoliated by chemical etching with iron nitrate and then transferred through favored film foil pre-coating process onto target adsorbing substrates. Coupled SEM and optical imaging, Raman mapping, and field effect transistor or FET analyses showed high monolayer purity and copper thickness independence for surface catalysis through self-limiting substrate solubility and saturation, and reasonable quality via room temperature extracted carrier mobility and residual Dirac density, but less effective than mechanically exfoliated equivalents. A later commercial process developed larger inch scale films. Conducted in 2010, graphene was also found to be viable as an oriented materials growth template, yet inorganic molybdenum disulfide and phosphorine 2D materials were structurally favored for electronics application. These, of course, were other examples of graphene's application and diverse purpose. Further, mass and energy conversions are necessary, or at least considered in all physical processes. The materials industry attempts to direct such pure phenomena to support technology and thusly our sentient existence. As this inherent understanding of the universe has grown, its pursuit has inevitably arrived at maximized scale. Researchers and engineers are committing such accumulated knowledge to understand and apply processes at both parsec and Fermi scale distances. Both in expression and measurement, scale is relevant to all dimensions and intersection of its nature. Yet this challenge to our existence requires materials that are robust on all scales. Within the most recent centuries, purely two-dimensional or 2D materials have presented transcendent physical and chemical properties that will enable technology enrichment as supermaterials. Planar organic sheets composed of a carbon lattice called graphene maintain properties which are structurally unique to its monolayer architecture. As the first 2D crystal discovered, this molecule acts as the allotropic, i.e. structural source of derived 0D fullerene spheroids, 1D nanotubes, and the prominent stacked 3D graphite carbon allotropes. The densely conjugated bonding within this sheet is sp2 hybridized, as previously mentioned, allowing unique electron-electron interactions across the monolayer surface. The pz electron of the half-filled bonding and anti-bonding pi bands increases electron, i.e. charge carrier mobility. Therefore, unlike those shorter in metals, this semi-metal supports long-range interactions, which affect various properties, particularly electrical energy band conduction. More specifically, considered a zero-gap semiconductor, carrier energy is not constrained to promotion across the energy gap between discrete filled valence and empty conduction bands. This phenomena occurs via Dirac points, through which the electrons behave as quantum holes for such conductive scattering effects. Dirac points represent this continuous band as band cones, showing electron-electron range with greater interaction velocity near the cone intersecting Dirac point as curvature, when in an undoped charge-neutral valence-occupied state. This phenomenon has been detected via angle-resolved photoemission spectroscopy. So, due to such distinct conductivity, this material maintains the highest known current density, exceeding that of copper by a 1,000,000-fold factor, as well as intrinsic semiconductor mobility. Both conversely and expectedly, resistivity is also lowest for graphene. Additionally, graphite thermal conductivity is greatest, while that of the similar 3D allotrope graphite is smaller by a factor of 5. As the thinnest material at 0.345 nanometers, graphene density is very low. It is gas impermeable even to helium, yet its relatively high absorption of visible electromagnetic radiation is also governed by the low energy structure evident at Dirac points. Through this low density, largest volume surface ratio is achieved. Yet graphene is most thermodynamically stable in relatively large sheets at 80 nanometers or over 24,000 atoms. And its dense conjugation does not prevent flexible extension of the planar surface. Graphene is mechanically harder than carbon allotropes of homogeneous diamond crystals and heterogeneous steel alloy. Some of these properties are collectively demonstrated by a theorized, nearly optically invisible graphene hammock supporting the mass of a house cat at 4 kilograms, with hammock mass being that of its whisker less than 1 milligram. Although inert, absorbing groups may be functionalized onto its surface, as well as stacked in graphitic form for specialization, and if damaged, self-repair occurs under simple exposure to organics. Graphene was initially detected as electrical conductivity differences of intercalated graphite in the 1960s. Through this technique, the sheets were isolated by large salt molecules, such as a potassium salt containing THF and an organic carbon chain in NMP solvent. However, complex techniques conducted from 1859 to 2004 were unable to discern graphene crystals, yet a simple method was finally able to do so only recently. In 2004, a novel crystal isolation method called micromechanical exfoliation was implemented to cleave the graphene crystals using common adhesive tape from a natural pyrolytic graphite surface. This effective technique finally allowed further investigation of the unique crystal properties as previously discussed by the reproducible flakes generated. This cleavage technique exploits the much weaker intersheet van der Waals interactions than those of the intra-sheet covalent character within the stacked graphite architecture. Such isolation method progress was indicated by the exponential research publication interest trend following this year. By 2013, China had claimed 2,216 inventions, while the United States earned 1,305 inventions, and South Korea obtained 684. However, patents claimed by respective company were 422 by Samsung Electronics, 167 IBM, and 124 LG Electronics. By this activity, interest in graphene has been rapidly growing, with acute emphasis in the electronics industry. The domain of electronics comprises both diverse and broad applications. Graphene has been used in electrical devices, sensors, energy storage, and composites. Yet application delimits necessary quality and scale of the material. Quality will be defined as monolayer purity in this topic survey. For example, electrical devices such as field effect transistors, or FETs, require high quality but small area parameters. But conductive coatings only demand low quality and area. However, touchscreens and solar cells require both high-quality and large-scale films. The execution of maximized scale is a synthesis challenge for commercial application, but the chemical vapor deposition, or CVD method, has shown success. And other techniques, such as reduction of graphite oxide and carbon nanotube unzipping, have been employed for the respective limited applications mentioned. Synthesis methods are also diverse, but some additional examples are liquid phase extraction, epitaxial growth on electrically insulating substrates such as silicon carbide, and of course exfoliation. Exfoliation competes with CVD in terms of quality, but is not a scalable technique. The final substrate transfer process of CVD is also favorably arbitrary and thusly not limited by application. CVD synthesis can be performed on multiple substrates, including transition metals and through various organic vapor ligands under many conditions. But in 2009, the CVD method was established to produce large films on a copper foil substrate and were successfully transferred onto other arbitrary substrates. In this experiment, graphene films were primarily grown on thin, 25 micron thick, 1 centimeter long copper foils using a hot wall furnace of fused silica tube, 22 millimeter inner diameter, heated in a split tube configuration. Foils of 12.5 and 50 micrometer thickness were also considered, where multiple runs were performed using each thickness. The growth process began by evacuation of such foil-loaded tube whose original pressure was replaced by that of hydrogen gas at 40 millitorr, added at a maintained flow rate of 2 sccm for the entire process at 1000 degrees Celsius. The temperature of the copper foil substrate was finally stabilized at less than or equal to 1000 degrees Celsius during this typical conditioning pre-process time interval of about 60 minutes. And then the gaseous methane carbon source ligand was introduced to this copper surface at constant flow rate of 35 sccm and total pressure of about 500 millitorr. This growth process principally occurred over a 30-minute interval under isothermal and isobaric conditions and followed by furnace cooling to room temperature at about 60 minutes. This cooling rate was also considered from 40 to greater than 300 degrees Celsius per minute. The synthesized graphene films were separated and transferred from the copper foil substrate during the subsequent substrate dissolution process. Aqueous iron nitrate solution was used to exfoliate these produced films through chemical etching. This effective etching interval was determined by etchant concentration as well as foil area and thickness. Usually, a 1 square centimeter, 25 micrometer thick copper foil was dissolved by iron nitrate overnight, but this was at low concentrations of 0.05 grams per milliliter at about 16 hours overnight. But this chemical exfoliation process collected 2 films from both sides of each copper surface. The final substrate transfer step considered 2 similar approaches. Films were adsorbed from the dissolved substrate by contact onto the arbitrary one, and in the other approach, the film foil system surface was first coated with polydimethylsiloxane, or PDMS, or polymethyl methacrylate, or PMMA, and upon copper dissolution, the remaining coated graphene was transferred by adsorption from solution, as above, or as previously mentioned. Further, this coated transfer method was derived from, and therefore similar to one that was also based on etched exfoliation. In that original technique, detachment of coated PMMA graphene as a system from the initial substrate was performed by mere partial etching of the substrate, or silicon dioxide, by sodium hydroxide at 1 molar concentration in an aqueous condition. A room temperature water bath allowed manual detachment of this membrane by peeling upon this release. The graphene was then transferred to the target substrate by dissolving the PMMA with acetone, while superimposing this final substrate. The morphological and conductive properties of the produced films in this reviewed experiment were then primarily determined by coupled scanning electron microscopy, or SEM, and optical imaging, which consisted of SEM and TEM. Mapped Raman spectroscopy on surface oxidized silicon substrate, and fabricated field effect transistor. However, to summarize the growth and transfer processes, the graphene films were grown on thin copper foils by direct surface catalysis. Hot wall furnace of a fused silica tube was used as the oven source of heat, and iron nitrate etching exfoliated films during substrate dissolution. The growth process consisted of the tube being evacuated and then backfilled with gaseous hydrogen. The stabilized copper temperature was next, and then the gaseous methane was introduced at certain flow rate and pressure over a given time, that under isothermal and isobaric conditions. There was cooling to room temperature. And then for the transfer process in this experiment, the system coated with PDMS or PDMA in solution occurred next. And then after the copper dissolved, the coated graphene was lifted from the solution. And then upon this, the subsequent transfer to new substrate of the surface oxidized silica dioxide was the final step. And the typical growth profile by condition is shown, which summarizes these steps and the critical growth phase. The coated transfer method was derived from a similar method as mentioned. It was also based on etched exfoliation. And as previously described, in summary, there was a detachment of the coated PMMA graphene by a partial etching of the substrate, silicon dioxide. The water bath was used for manual detachment by this peeling process, and then transfer was to a superimposed target substrate. And these steps are summarized in this graphic, or this figure, I should say, as the original wet graphene transfer process. So in terms of the conclusions of this experiment, we will begin with the results of it. The CVD deposition mechanism was expected to be precipitous, by which foil thickness would determine surface layer density. Yet, this behavior was not observed in this experiment. Imaging analyses instead presented monolayer purity greater than 95%, and foil thickness independence of a surface catalyzed process through self-limiting copper substrate solubility and saturation. Raman mapping indicated characteristic approximate 0.5 G to 2D intensity ratio, where the G represented graphene structure and the symmetrical 2D band represented typical 2D planar structure, as well as low defect intensity, which was represented by the D band. Additionally, the dual-gated FET device was constructed using a double layer of graphene separated by a thin layer of aluminum oxide dielectric material. The subject graphene showed reasonable conduction by room temperature extracted carrier mobility of the order of 10 to the third and residual Dirac density of 10 to the 11th, but was notably less effective than the mechanically exfoliated equivalents, which were respectively at the 10 to the 5th order and 10 to the 13th order. So there was reasonable success. However, in these figures, the effective deposition of graphene is shown through the gloss of the film, as you'll note. Also, in the second figure, SEM and SEM morphology and transfer onto two different arbitrary substrates are shown. The SEM image represents a 30-minute duration, growth period, I mean. And finally, in the last SEM compilation, oven duration was shown to affect the film growth or the coverage of the foil surface. And as you will note, it increases but then saturates after 10 minutes, where these images depict 1 to 60 minutes. As mentioned, the figure on the right, figure 16, represents the FET device and its resistance versus top gate voltage, or VTG, and also in terms of the VD Dirac top gate voltage, which I would assume would be at the Dirac point measured, in terms of backgate voltage with the model fit, which is represented by the solid line. So overall, coupled analytical methods determined film quality, which was essential for this very thin surface that could be prone to such defects. So coupled methods really did show a true confirmation of the properties. In the left figure, or figure 15, there is an SEM image in A, a microscope contrast uniformity depiction in B, but and also in D, E, and F, the DG and 2D mapped Raman peak bands are represented. However, the subset C seemed to be the most relevant to me. I mean, the colored indications in A and B were represented through C, which show the 3 different layers and how they are affected by the intensities and their characteristic ratios for such structure. Specifically, the Raman mapped layer bands and characteristic band shifting and ratios are presented in the subset C, or Raman shift, and intensity versus Raman shift. And finally, commercial viability is a necessary consideration for development of new technology. A later 2010 commercial process was developed and derived from these growth and transfer techniques, resulting in larger 1-inch scale films, also of high quality. The adhesive roll-to-roll transfer by polymer support enables rapid dry transfer and rinse etching. This method was applied through fabrication of low sheet resistance and high transparency doped 4-layer transparent electrodes, which were therefore superior to commercial ones of indium tin oxide material. High-strain functional touchscreen panel devices were also produced using this process. In conclusion, graphene has pioneered the path for 2D supermaterials through research and industrial endeavors promoting maximized scale. In terms of novel application, graphene was also found to be viable as an oriented growth template for various materials, supporting electrical applications such as solar cells, supercapacitors, lithium-ion batteries, and photocatalysis. Through these respective roles, graphene acted as a growth, self-assembly, and sacrificial templates separately, as well as contributed to surfactants, or surface active agents. Such agents are used to mitigate interfacial surface interactions. Despite the diverse properties and thusly robust applications of graphene, inorganic 2D materials such as molybdenum disulfide and phosphorine structurally compete for preferred electronics behavior with engineered graphene oxide via carrier mobility, produced area, high device on-off ratio, of the molybdenum disulfide, as well as tunable band gap of phosphorine separately. The research interest trend has been similar to that of graphene as well. Therefore, 2D materials largely afford unique properties to their application and have established a structural basis for the future of materials technology. And with that, thank you for your time and for considering this presentation. I did enjoy learning these properties of graphene, and thank you for the opportunity. And my name is SBrody. Thank you again. And of course, multiple references were used to develop this work and to really embody the breadth of the efforts engaged in graphene. However, there were many more synthesis techniques and conditions within them that should be scrutinized in further surveys. But for the scope of this work, which was truly a survey of methods before the CVD on copper technique, as well as after, I believe that the requirements were met for a proper survey. Again, thank you for your time and for your consideration.